Good morning, students. In today's lectures, we'll talk about the computer-aided design in restorative dentistry as an overview of this class. And I will add some complementary material in the ETL site so you could refer those materials if you want to remind some basic rules of occlusal surface of the tooth morphology. It will be provided in Korean lectures, but it will have some subtitles in English and Vietnamese, so you can get help from those materials. As 3D printing, computer-aided machining, and optical scanners keep improving and are becoming more accessible, design software is rapidly becoming the next frontier in digital dentistry. Rapid prototyping technologies in dentistry were initially operated with generic software that was not specifically designed for dental applications. This was very inefficient and a limiting factor for digitalization of dentistry. The arrival of specialized software for different dental applications has made digital dentistry a reality by making it efficient and bringing it to its full potential. Today, I will introduce the different types of software that has been developed for restorative dentistry. This includes software for fixed, removable, and implant prosthodontics, as well as software for treatment planning. Computer-aided design is a fundamental step in any dental intervention involving digital technologies. Images registered through different acquisition systems such as scanners and CBCTs are managed in specialized computer files, able to store 2D, 3D, and even color information. These files can then be processed with specialized software in order to virtually plan treatments and design prosthetic restorations. The main types of computer tools and files that can be used to plan and design restorative treatments will be addressed today. This type of software can be used, for instance, by dentists to plan aesthetic and implant cases in the office, or by dental technicians to design prosthetic restorations in the laboratory. To begin with, I will talk about 2D photography as a digital smile design tools. Dental treatments requires aesthetic and functional predictability. In this context, restorative treatment planning should integrate the aesthetic framework of the patient's face and the dynamics of smile, mastication, and phonation. Digital smile design, originally proposed by the Coachman and Calameda, pursues two-dimensional analysis of the smile through intraoral and extraoral videos and photographs. Undoubtedly, this resulted in a palpable improvement in digital cases planning. Treatment objectives such as the corrections of the incorrect tooth proportion and analysis of tooth form and size in relation to the facial profile in smile and resting positions were achieved thanks to digital design of the smile. Communications with the patient regarding the projected treatment outcomes was also improved by the application of the digital smile design because it provides the dentist with a visual tool to discuss patients' wishes and expectations prior to therapy. The digital design also allows the multidisciplinary teams to better assess the prospective treatments. For example, periodontists may benefit by digitally outlining the border of the gingivectomy required for the crown lengthening procedure, which makes it easier to coordinate with the restorative treatment. The communication of the expected results with the laboratory is another advantage of the digital smile design by providing the technician with the dimensions, shapes, textures, and contours of the restorations planned by the clinician, integrated with the face and smile of the patient. It's a kind of key information often overlooked by dentists and dental technicians. Digital design consists of the performing first a digital facial and dental analysis on which the horizontal bipupillary, nasal, and labial commissure lines are marked, along with the smile line. Digital design on two-dimensional smile photographs should be taken into account three important issues: the size of the photograph, to correlate the extraoral photographs with intraoral ones, the parallelism of the photo with the horizontal plane, and the position of the incisal edges and the position of the midline. After correlating this information, the size of the teeth is determined by an appropriate proportion for each patient, taking into account the visagism, which consists of a series of characteristics related to the patient's biotype. The visagism is a kind of proposed novel concept, make it possible for the patient to express the desirable emotions and personal traits through their smile. According to this concept, clinicians can design a smile that blends with the patient's physical appearance, personalities, and desires. The teeth taken from a virtual library including various morphologies, such as triangular, square, ovoid, are adapted to the digital design, and after calibration with the digital ruler, the new dimensions and proportions of the restorations are determined. This includes the dental axis, its relation to the smile line, gingival margin, face midline, height of the interdental papilla, and incisal embrasures. Digital planning can be of two types. The first one is additive, which usually involves the reversible changes by adding restorative materials onto the remaining tissues. The second one is a subtractive ones, which involves irreversible changes by eliminating hard and soft tissues to achieve an expected result. Once the design is determined, a report is prepared for patient's approval. The fabrication of the physical form makes the digital planning tangible and more real to the patient. This is usually done by preparing a diagnostic wax-up based on the predetermined measurements and then using a rigid condensation silicon matrix to copy the wax-up and fabricate a temporary restoration that can be transferred to the patient's mouth. Two-dimensional analysis of smile is gradually being replaced by three-dimensional smile analysis, which could perform digital simulation by incorporating depth as a third dimension. Moreover, integration of the 3D images of the face and the smile of the patient with the planned restorations enables more predictable facial guided digital smile design and simulations. Scanned 3D images of the face and the dental arch are correlated to make a digital design that then must be materialized so that the patient gives his approval or disapproval to avoid inconveniences with the final result of the treatment. These results can even be integrated directly into the digital workflow, designing and machining the mock-up, temporaries, or even the final restoration using CAD/CAM technology. In order to evaluate the result, the mock-up can be presented to the patient. There are several types of software in the market, from the simplest ones like Keynote, PowerPoint, and Photoshop, which allow a two-dimensional analysis, to other more specific ones, such as RealView from 3Shape, Nemotech, Smile Design from Cirec, and so on, that directly facilitate the entry of the obtaining training and allow a simplest workflow. In conclusion, the digital smile design is a concept of diagnosis and reversible planning and susceptible to modifications of clinical cases during the execution of the treatment. It contributes to improving the communication among the members of the patient care team, such as doctor and technician. In addition, it facilitates communication between the dentist and the patient. The digital smile design is a valid tool for documenting and archiving clinical cases in orderly manner. This concept should be handled with carefully in order to meet the real needs and expectations of patients, as well as the intrinsic limitations of the dentist, his team, and the therapy. Finally, it should be noted that the digital smile design, a concept that requires learning, training, and understanding its fundamentals, objectives, and sequences. Now we will look into the 3D files which is used in the 3D CAD design in restorations. Patients' dental topography and morphology captured with optical scanners are usually saved in the form of the 3D image file that are crucial in the process of the treatment planning, execution, and documentation. There are different types of 3D image files, and it is important to know the difference among them. The best known and the most commonly used within the field of dentistry is the STL file, which may be very familiar to you. In fact, this kind of file was created by the company 3D Systems, and the acronym stands for the stereolithography or standard triangle or standard tessellation language. This type of file stores information regarding the geometry of the given 3D object, but it does not include information regarding texture or shade. For this reason, this file is not excessively popular beyond the field of dentistry. Another limitation of this kind of file is that it does not include any metadata or personal information about the patients. For this reason, although this could be beneficial from a legal standpoint, there is a tendency toward replacing STL files with the files that store patient data such as DICOM files. Another commonly used 3D image file is the OBJ file, the acronym of the object, which was developed by Wavefront Technologies. Unlike STL files, OBJ files contain information on texture and color of the 3D object. They are used by some facial scanners in the field of dentistry. The PLY file is another 3D image file used in dentistry. It is known as the polygon file format or the Stanford triangle format because it was developed at Stanford University. This file stores graphical object described as a collection of polygons, and it contains the exact description of the object along with its color, texture, and transparency. Some intraoral digital scanners export the scanning data on this type of file. It is very important to mention that all of the aforementioned files can be encrypted as closed. This is often done by manufacturers in order to force the technician or the dentist to remain within the specific workflow in which all devices and software are supplied by the same company, including scanner, design software, and production unit. Now let's move on to the 3D design. After acquisition with a scanner, 3D image files can be imported to a design software that would have different tools for manipulating, editing, and designing the 3D model or the final future restorations. It is important to note that this software could be proprietary or open source and frequently includes a suite of different work models. Most design software are acquired in a standard version that allows to design common dental and implant restorations such as single copings or bridge frameworks or even, in some systems, post and cores. All systems have add-on modules that can be required independently, which extend the range of indications and design capabilities. From now on, we will discuss the main modules usually included in design software. The first one is a Smile Design. As described earlier, Smile Design software can process 2D photos and or 3D files of the patient face and teeth. It could also merge intraoral scans with the facial scans for more comprehensive results. With this module, the dental care provider can edit reference points and lines in order to determine the ideal dental proportions and select teeth from an electronic library to simulate the final results of the proposed treatment. The next one is the virtual wax-up. This module allows dental care providers, especially technicians, to create a virtual workshops of cases in a very efficient manner that replaces the traditional hot wax laboratory procedures. And our classes are focused on this point actually. And the next one, from these virtual workshops, physical mock-ups can be 3D printed for assessment in the patient's mouth. Besides their use for restorative mock-ups, this type of module is also used in design splints for surgical procedures such as crown lengthening. The next one is the tooth library, which is also important to our class. Usually, design software would include a library of different forms of teeth that can use across the different modules. These libraries can sometimes be expanded by incorporating additional anatomical forms from scanned teeth, which can be said as a novel innovation in the artificial intelligence era. The next one is the model builder or creator. This module is used to fabricate a physical model from a 3D file generated by intraoral scanners. The module would export the file for fabrication using a 3D printer or CAM devices. The operator can design the models to be hollow or reduce the printing cost, and with the detachable segments to facilitate handling. In implant cases, the models can be designed with the pre-made holes for the implant analogs and detachable segment for the gingival mask that are to be manufactured using a different type of material than the rest of the model. The next is a provisional. Various software modules can be used to design temporary restorations based on the preoperative scans. This type of software can be used to design the temporary restorations by replicating the original anatomy of the tooth, if acceptable, or by relying on in-house tooth digital libraries. The next module is also important to our class is a virtual articulator. This type of module is used to digitalize the relation between the upper and lower arch, replacing the traditional physical articulator. There are different types of virtual articulators with various degrees of automizations. Some of these software, such as the Zebra systems, can import and incorporate information on the dynamic movements of the patients obtained from a jaw registration system. The next one is a full denture. This type of modules allows technicians to fabricate complete denture digitally. The software can be used to design a denture base as well as other elements of the treatment such as the customized impression trays or base plates. It also allows to identify critical landmarks such as alveolar ridge, the midline, and the occlusal planes, and so on, and would propose a possible tooth setups that could be edited and ultimately exported for denture fabrication using 3D printers or milling units. Partial framework module. This type of modules is designed to replace the classical lab technician work related to the fabrication of the wax patterns used to cast metal frameworks of removable partial denture. This technology, in combination with additive manufacturing, allows for much faster and more accurate results than those achieved with classical manual techniques. Usually, partial framework modules consist of the paralleling tools to determine the path of insertion, identify the line of contour, and block out the undercuts, as well as additional tools to design the various components of the framework, such as major connectors, clasps, and occlusal rests. Moreover, this type of modules often allows to combine partial framework designs with crown and bridge design elements. The design generated by these modules are ultimately exported for additive manufacturing either by 3D printing bone-out wax patterns for subsequent casting or by direct 3D printing using laser sintering technology. The next is a popular module, which is named as the implant module. This type of module allows clinicians to diagnose and plan treatments with dental implants. The software can be used to combine radiological information with intraoral examinations by merging DICOM files from a CBCT with 3D files generated by intraoral and extraoral scanners. With these modules, we can design a surgical splint for guided surgical procedures and provisional restorations with different implant systems depending on the libraries available in the software. And there is a subsequent modules for implant modules as a implant prosthetic module. This type of module enables the design of the customized abutment and the prosthetic frameworks for both cemented and screw-retained implant-supported restorations. To be able to design these implant prostheses, the CAD software includes a library of different types of implant connections and scan bodies for digital impression that can be updated with new designs as they are introduced to the market. The next one is a bar module. This module usually includes a library of different types of bars that enables custom design of bars for overdentures. These designs can range from simple bars with standard cross sections such as a Dolder, Heather, or Ackerman sections to bars for complex cases where additional attachment and retentions can be added. Prefabricated attachment consisting of the cylindrical holes or even arbitrary geometries with various paths of insertion can be added to this design. As a subsequence, there is a bite splint module. It is possible to design Michigan or other types of splints and mouse guards with CAD software. Some software allows synchronizations with the virtual articulators module in order to adjust the occlusion of splint with the antagonist arch and optimize the final design. Okay, let's move on to the virtual tools in CAD software. All available CAD software systems have different tools for design automation. In fixed dental and implant prosthesis, CAD software can automatically detect the margin of the tooth preparation or implant emergence profile, the tapering of the abutment axial walls, the interocclusal space, the path of insertion, and the thickness of the final restoration depending on the material selected. In implant-supported prosthesis, the CAD software can control the path of insertion across the multiple implants and manage unfavorable screw access and malalignments of up to 30 degrees with tools such as the dynamic abutment solutions. The software can propose a design for the anatomy of the final restoration through mathematical algorithms by relying on the anatomy of the another tooth in the patient's mouth, as known as the bioreferencing, or by relying on a scan of the provisional prosthesis or the original tooth prior to extraction, also known as the biocopying. The two words, the bioreferencing and biocopying, should be remembered. Different virtual tools are available to improve the position and occlusal context of the restorations by allowing the operator to move, stretch, and rotate them, as well as by adding or removing material and smoothing the surfaces. In overdentures, complete dentures, or removable partial dentures, the CAD software can help identify the flange, the tuberosity, and the retromolar areas, as well as the final position of the teeth in the prosthesis. All CAD systems are able to export the design as a portable document format, as known as PDF. With this file, the dentist can evaluate the design and validate it. This tool is very useful to improve the communication between technicians and clinicians. When the final design is accepted by the clinician, the lab technician can use a CAM software to nest the restoration in the block or disc of material to be milled and control the manufacturing strategy. In the case of additive manufacturing techniques, for example, laser sintering deposition, it is also possible to determine the location of the restoration, the number of layers, the width of every layers, and so on. Now, I will introduce the CAD software currently available. There are different programs available for dental CAD that include the tools and applications described earlier. Now, we will discuss the best known available softwares. The first one is the Dental Systems. Dental System is a software created by 3Shape, a Danish company. This software has a suite of add-on modules with a wide range of indications that include all the modules mentioned earlier. Dental System has a powerful work module for digital smile design known as a real view, whereas the 2D and 3D information is combined, obtaining very real photographic montage, which helps in planning the case and communicating with the patient. Dental System can import STL files from different extra and intraoral digital scanners. The design obtained with the software can be exported to an open STL file for manufacturing in any milling unit, laser sintering unit, or 3D printer. It is worth mentioning that if you scan intraorally by using their own company product, as known as the trios, the 3D information obtained is stored in the proprietary format called IMG that not only contains the STL information but also the texture and color of the different surfaces of the patient's mouth. Dental System is available for purchasing in different versions, from a premier version that includes all the models to more basic versions. Recently, 3Shape has created a specific design software for clinicians known as the Dental Studio. The software is intended for designing simple restorations that are manufactured with chair-side milling units in a single appointment. The next one is the DWOS, which is abbreviation of the Dental Wings Open System. It is a CAD software from a dental wing company which was founded in 2007. The open architecture of this CAD software allows users to work with clinical information, design processes, and downstream production processes. This software has a wide range of modules, materials, implant libraries, and anatomies. DWOS can be used in combination with the Co-Diagnostics CBCT planning software in order to link radiographic data with intraoral or extraoral scan data to optimize the implant position and final design of the prosthesis. In addition, this software has a version for dental lab and another one for clinics, which allows dentists and lab technicians to work together in real time. The next one is the Dental CAD. This software was created by the ExoCAD company, which was founded in 2010 as a spin-off company from Fraunhofer organizations. The software was developed for dental technicians, and it has a wide range of indication, functionalities, and work modules. With the standard version of ExoCAD Dental CAD, the lab technician can design anatomic crowns, anatomic simple copings, attachment, bridge frameworks, inlay, onlays, veneers, and wax-up, and telescopic crowns. Moreover, with add-on modules, it is possible to make more complex work. The acquisition of these additional modules is flexible and can be done according to the needs of the lab technician without the need to acquire all of them. More recently, ExoCAD has developed a simplified version of the software for use in the dental office that can be used to prepare chairside with different milling units. ExoCAD is an open software that can easily incorporate free libraries of foams and implants, and it produces the design in open STL files that can be manufactured with any CAM system of additive or subtractive technology. For these reasons, many manufacturers and distributors of extraoral scanners have partnered with this software. The next one is the InLab and Serac. Sirona has three design softwares: the software InLab for dental labs, the simplified software Serac for dentists, which is coupled to an intraoral scanner, and the premium software Serac, which is a software for dentists but with almost identical features as the InLab version. The SW InLab software includes a basic configuration as well as additional modules for removable and implant prosthodontics, respectively. The basic configuration can be used for many indications such as inlays, onlays, veneers, crowns, and the digital smile design. The module for removable prosthesis enables the design of all types of removable prosthesis, as well as splints and custom trays. The implant module allows the lab technician to design implant-supported prosthesis and surgical splints for guided surgery in implantology. The chair-side version of the software was originally developed by the Borman and Brandestini in 1985, and it is the first CAD/CAM dental system used in the world. Nowadays, it consists of the complete digital CAD/CAM solution that is the easiest to use for chairside restorations. It is integrated with an intraoral scanner and a chairside milling machine for design and manufacture of dental restorations and screw-retained and customized abutment restorations for single implants and simple surgical splints. In conclusion, computer-aided design software is rapidly replacing many of the manual procedures performed by dental technicians, and by doing so, it is transforming the profession and the dental laboratories. Many laboratory procedures such as the wax-ups, mounting models in articulators, and preparing frameworks for removable partial dentures can now be done virtually using specialized software. In addition, pre-designed teeth and prosthetic components such as implant bars and abutments are available in the form of the virtual digital libraries that can be used for facilitating treatment design. In addition, specialized software is also penetrating the dental office by facilitating aesthetic treatment planning using smart design software, in-office design of the permanent and temporary prosthetic restorations, and treatment planning of implant surgeries and prosthetic rehabilitations. Okay, that's it for today. See you next week. Thank you for watching.